там кучу кнопок давить, но вроде как... Сказано, что лиф у нас уже есть. Теперь только надо докладчика дождаться. На самом деле общался с ним Лука в основном, поэтому если что там пойдет не так, то он, наверное, будет в первую очередь стучаться к Луке, Лука будет стучаться к нам, ну и так далее.
Where is Luca? He's not here.
Yeah, we should switch to English, sure, yeah.
Sorry,
Luca,
sorry.
not here yet, but I believe he will come. I hope.
У меня, I have a small headache today after a bottle of champagne last night. Hello, Kelly.
Friends, I hope you're all okay.
Thanks.
Okay, very good.
Good afternoon. So you're the co-host now. You can. This will allow you to share screen.
Okay, let me. Hang on just a second. I have to remember how to do this.
And what I don't know, have Luca asked you or not? Is it okay with you that it is live streamed on YouTube and then we keep it recorded?
Fine.
Great.
Yeah, no problem. So
very good, thank
you. Just sorry. Let's see, where's the share screen thing gone? This is not Zoom. I'm not so used to Zoom. Where is share screen?
Well, to me, it's just in the middle, at the bottom, this green button, which...
Oh, share screen. That's green. Okay, yes. Yeah, and I share the desktop rather than anything else.
Yeah, I think you should. Yeah, now we see your screen. Yeah, indeed.
Do you want... no, it's okay.
And then I have this thing on the side. I don't know if do you see that thing?
No, we don't see. This is just for you.
Okay.
It's somehow Zoom smartly cuts it for everyone.
Right. Oh, I see. It's gone. It's now gone in the bottom. Okay. So let me just see, I don't actually see my whole slide. How do I deal with this? Yeah, can I make this small or something?
Just to push escape?
Yeah, you mean the thing on the right?
Yeah,
well, actually, I don't remember how you do it smaller, really.
Hide?
Something kind of one-line button at the top of this thing where you can minimize it somehow.
I've minimized it, yeah.
Yeah, it's the best what you can do. It doesn't allow you to get rid of it completely.
Okay.
Somehow you may want to switch to someone else. I don't know. So it's Zoom feature which is beyond our control for sure.
Yeah. Okay. All right.
And by the way, regarding questions, is it okay if people interrupt you in the meantime, or you prefer to keep it?
Yeah, sure.
Okay, good.
Just make sure. Let's see, I just check one thing. hang on. Wait. Okay, I guess that's all right.
I think we can wait a couple of minutes, okay?
Sure.
Because people are still coming. Okay, 1:25. So, hello everybody. Today we have a pleasure to have a talk by Kellogg Stelle. He will tell us about localizing gravity and supergravity on brane worlds. Please, 1 hour.
Okay, it's a pleasure for me to be giving this this talk. I don't know exactly where I'm giving the talk, whether it's in Moscow or Nordita or other places. But anyway, I'm happy to be involved. What I want to talk about is the nature of effective theories on the world volumes of brane solutions in supergravity. This basically work that goes back some time, earlier with Ben Crampton and Chris Pope, and more recently with my students, Alex Harold, Chris Erickson, and Rahim Leung. So let me just give you a picture of what one might consider a traditional type of compact space dimensional reduction. This actually is from an exposition, in fact, in the Modern Art Museum in Tel Aviv that I saw that symbolizes pretty well the notion of reduction on spheres. And we'll come back to that later on in a minute. It's actually relevant to some of the points I want to make. But so the main topic here is when you have a brane with a transverse space that is infinite in volume, in what sense can you consider that you have a localized gravity on the world volume? So there are going to be two notions of localization that are going to be relevant to this talk. And the first one involves, the notion of consistent Kaluza-Klein reductions, I think, should be familiar to most people. Generally speaking, one talks about such consistent reductions with a compact transverse geometry. In this case, the transverse geometry is non-compact. And in fact, it is going to have the structure of a brane solution of supergravity. And so I'll call that underlying brane solution the skeleton of the generalizations that we're going to be considering. So what we want to talk about is a lower dimensional world volume theory. And what we're going to find is that it's actually, you can extend this to a full supergravity theory on the world volume with a degree of supersymmetry that the brane skeleton vacuum solution possesses. And then all fields in the underlying brane skeleton extend into the the transverse higher dimensions, which remains fixed structure. Now, then there's a second type of world volume gravity, which is a more full localization of gravitational phenomena near the brain, falling off towards transverse infinity. And this generates an effective massless lower dimensional theory, but it is not in the same sense as the first type that I just referred to above. It is not a consistent Kaluza-Klein reduction. Now, the word consistent, of course, is not necessary in order for it to be physically interesting. Inconsistent truncations simply mean that you can't just set all the higher modes to zero, but they maybe give rise to subleading corrections. There can also be an unusual type of symmetry breaking in such a theory, starting at fourth order, which we called covert symmetry breaking. That's not actually the main topic of this talk, however. Now, let's come to the first situation, which starts with a brane solution. And the brane solutions will have some subset of or subspace of the higher dimensional supergravity, in which the geometry is flat. So that's what we call the world volume. And what's been known for some time, since the work of Brecher and Perry back in 1999, is that for such a flat world volume solution, it is possible to generalize it to a solution where the world volume has a metric that is not flat but Ricci flat, and it still works. That's still a consistent solution of the higher dimensional theory. And of course, once you realize you can solve world volume solutions with r mu nu equals 0, of course, Stephen Hawking's ears pricked up and he realized, aha, let's play with black holes. So there's a paper by Chamberlain, Hawking, and Rial, which involved black holes on the world volume of such a solution. But of course, since the underlying brane solution is still there, it extends into the higher dimensions. And in their case, they looked at a 5-dimensional situation with a 4-dimensional world volume. The extension into the fifth dimension they called black strings. Now we're going to consider situations with more transverse dimensions, typically with spherical symmetry in the transverse dimension. So a more appropriate general image might be black spokes rather than black strings. Now, about supersymmetry, if there is some surviving supersymmetry in the flat world volume brane solution, Honglu and Chris Pope showed that one can make a consistent embedding of supergravity theory into at least the near horizon geometry of that brane solution. For example, for D3 brane would be ADS 5 cross S5 in type 2b supergravity. And what we're going to see is that this near horizon embedding can be extended, in fact, to a consistent full embedding on the brane solution throughout the higher dimension, not just in the near horizon region, but in fact in the full theory, full solution. So that's the sense in which the underlying brane is going to be the skeleton of this reduction ansatz. So let's just see, in terms of a simplified model, how gravity phenomena can be embedded. First, consider a model system in capital D spacetime dimensions with a metric, a p plus 1 dimension form gauge, p plus 1 rank form gauge field, and a scalar as given here, with the following equations of motion. Now, we will consider an ansatz for the metric, the warped metric form, as given here. I don't know if people can actually see. No, they probably can't. Yes, the pointer, perhaps you can see. So we have warp factors. Y are the transverse directions. X are the world volume directions. The metric on the world volume here is called G bar, G mu nu bar. And the metric the underlying metric in the transverse directions is called Gij tilde. So if you make such a construction ansatz for the overall higher dimensional metric, then you obtain the following Ricci tensor components as given here, where R bar is the Ricci tensor for G bar and R tilde is the Ricci tensor for G tilde. And so these involve the various covariant derivatives of the warp factors A and B. And so we start with a solution, which is a brane solution. In the standard branes, both the G mu nu metric and the Gij tilde metric would be, in fact, flat. So G mu nu would just be eta mu nu, Gij tilde would be a delta ij. And that is what I say here at the bottom, that the vacuum brane solution will have G bar equals eta. But you can see from the above construction that if you just cause R bar, the Ricci tensor in the world volume underlying G bar metric to vanish, then the construction still works, because as long as the A and the B functions, warp factors, retain the same structure as in the vacuum solution. So this is basically the observation of Brecher and Perry, that you can generalize world volume flat metrics to Ricci flat metrics, and that still works for a solution of the higher dimensional equations of motion. For the form field, of course, there's a corresponding part of the solution. Now, for supersymmetric solutions, there are extremality conditions, and when all is said and done, you impose these. You boil it down to a Laplace equation for this quantity involving the phi field. Remember, phi was the scalar field of the simplified model. So this h is exponential of constants over 2a times phi, and therefore this has to be a Laplace solution, and that is the giving rise to the basic brane solution underlying all of this. And in fact, because it's a Laplace equation, you see also this corresponds to zero force multi-brane solutions, because you can sprinkle Laplace solutions in the transverse space any place you want, and you get analogs of the Madame-Darpah-Petru multi-black hole solutions of Einstein-Maxwell theory. If you take advantage of the possibility of generalizing both the world volume G bar and the transverse G tilde Ricci flat metrics, then you can call this the solution doubly Ricci flat. But in the following, I want to concentrate mostly on what happens when you promote the world volume eta mu nu to a G bar mu nu world volume. And so what we know is that if you just make that Ricci flat, the solution still works. Now, the question is, what happens within a supersymmetric theory? Can you extend that to a full world volume solution with supersymmetry? Now, providing the vacuum solution with G bar equals eta preserves some degree of unbroken supersymmetry, then this Ricci flat gravity on the world volume that I've just referred to can in fact be generalized to an arbitrary solution of a world volume supergravity theory, where the degree of supersymmetry of the vacuum becomes the amount of supersymmetry of this world volume supergravity. So this, in fact, is a Kaluza-Klein consistent truncation onto the world volume lower dimensional supergravity. And the way that we found how this works is to study the two asymptotic regions of the underlying brane structure. There's an interpolating soliton structure where the underlying brane interpolates between flat space at infinity and another solution in the horizon region. For example, ADS5 cross S5. And that's exactly what I've just said here by studying how Honglu and Chris Pope constructed the ADS5 cross S5 near horizon reduction. Well, that's in fact a standard sphere reduction. So that comes back to, in fact, to my initial picture of the sphere reductions. Here we have, so this is an implementation of an asymptotic version of what we want to do in the near horizon geometry. So this now is in fact the near horizon geometry of the D3 brane. But in itself, what Hong and Chris did is not a full reduction onto the brane solution, but it suggests some of the technical tricks. Now, I'm not going to actually go through the details of this. In any situation where you're being presented with a claim of a consistent truncation, if you are handed the result of how to make the ansatz, all you have to do is go away and check it. So our hard work was in actually deriving the ansatz and then verifying that it works. And I'm merely in this section of the talk, going to present you with the result. So we have the following ansatz given here for at least the bosonic sector. We have not yet extended this into the fermionic sector, but that can, I think there's no doubt that can also be done. So we have a D3 brane of type 2b, and it has it's a 1/2 BPS solution. So one expects a 16 supercharge supergravity on the world volume, and it's a 3 + 1 is 4-dimensional world volume. And here, in fact, are the details. So as I've said, I've simply presented the results, and the result is that this works, right? This, in fact, allows you to have now arbitrary solutions of the n = 4 supergravity theory on the world volume. Anything you want to do with that within that theory then can be lifted up to a solution of the full 10-dimensional theory by a consistent truncation lift. Okay. Now, I've mentioned the notion of spokes earlier on. So similar constructions will generalize a variety of brane vacuum solutions with unbroken supersymmetries to similar Kaluza-Klein consistent Ansätze with supergravities with the corresponding supersymmetries. One can do the same sort of thing for N5 branes, and in fact, this leads us to a conjecture that this is completely general. This is not something, as far as I know, that's ever been proved, but it is something that has emerged from the explicit constructions that we've made. It looks like that whenever you have a brane solution with an unbroken supersymmetry of the flat brane, that this can be, in fact, generalized to a perturbed brane with an arbitrary nonlinear solution of the corresponding supergravity with that same degree of supersymmetry of the underlying vacuum. Okay, now these are all going to be on the skeletons of the underlying brane. Let's say that the A and B warp factors are going to remain unchanged. They're functions just of the transverse coordinates, and these are not being modified in these solutions. Only the world volume, what I called X dependence, is being generalized. Question: do these amount to a genuine localization of supergravities on the world volumes? Well, in a certain sense, because these are branes and they're falling off towards flat space as you go towards transverse infinity, not much is happening out at infinity. So there is a certain sense that these are localization of all the interesting part of the solution on the world volume. However, there is an issue that was already pointed out by Hull and Warner back in the 1980s about the separation of this lower dimensional effective theory from the rest of the theory viewed from the higher dimensional point of view. Now, another point about this is that, so as I've said, you can take an arbitrary solution of the world volume supergravity with the amount of supersymmetry that is given to you by the vacuum. And if your sources are taken purely from within the world volume supergravity, for example, in the case of Chamberlain, Hawking, and Rial, they were interested just in black holes. And so they threw away everything else but the metric and looked at Ricci flat solutions. So this is going back to the original paper of Brecher and Perry. And they had black holes on the world volume, which they then described as black strings extending into the higher dimension. And in more general spherically symmetric situations with more transverse dimensions, you could see this as black spokes. But the true test of localization would involve a full perturbative analysis of the transverse wave function spectrum. For example, does it form a continuum because it's infinite in volume? So you anticipate that the transverse wave function spectrum will form a continuum, and it might form a continuum right down to zero mass. Therefore, the Newton constant that that you would get for coupling to anything outside the pure supergravity theory would have a vanishing Newton constant. And that's the problem that Hull and Warner emphasized for non-compact Kaluza-Klein Ansätze. Given the reference there, I mentioned also the tri-man discussion of Mike Duff, Lev Okun, and Gabriele Veneziano about the meaning of Newton's constant in various and the number of dimensional constants in general in physics, in order to point out that there is a very special circumstance of pure gravity and of pure supergravities with regard to Newton's constant, namely that if you look at solutions purely within these classical supergravity theories, pure supergravity theories, there is no meaning to Newton's constant. It's just as in R mu nu equals 0, it's a self-interacting theory, it's nonlinear, and yet there's no meaning for the Newton's constant there. And that's related to the fact that there is this scaling symmetry of the Einstein theory, which in fact gives rise to the one parameter family of black hole solutions, with the mass being the integration constant. So for pure gravity, pure gravity, R mu nu equals 0 only, or supergravity theories, there is in fact no meaning to Newton's constant. It only arises, a meaning arises only when you try to couple to something outside its core theory. And in many situations with non-compact transverse spaces, the resulting Newton's constant for coupling outside the core theory vanishes because of the infinite volume of the transverse space. So a true localization would be something which avoids this problem. It would involve a bound state wave function that's normalizable of the transverse part of the solution, and preferably not only normalizable but also separated from the non-compact continuous spectrum by a mass gap. Okay, so now here I'm going to present, this is really the second topic, of an approach to achieving exactly that. This starts with the Salam-Sezgin theory and its embedding. This is also a kind of a brain, but it's a very particular structure that Abdus-Salam and Ergun Sezgin gave us back in 1984. So this particular structure involves minimal supergravity in 6 dimensions, coupled to a two-form tensor multiplet, super Maxwell multiplet, and gauging, this is important, gauging the U1R symmetry of the theory. And then the Einstein-Maxwell system has the following bosonic Lagrangian given here. Now, you see there's this Einstein action, there's the F mu nu term, there's the tensor kinetic term, and then there's this field phi, the scalar, which, however, has a potential here. Note the sign of this potential is important. It's unusual in supergravity, in supersymmetric theories. This potential is negative in the Lagrangian, therefore positive when it's in the Hamiltonian. And that's a key feature of R-symmetry, gauged R-symmetry models. This is the Salam-Sezgin model itself, and also with a generalized family of models with non-compact symmetries. And for example, you can fit this into a more general class of models with SOPQ over SOP cross SOQ structure for the scalar sector of the theory, is found by Bergshoff, Chong, and Sezgin, and also with the student Tom Pugh and Ergun and myself back in 2005, 2010. So now let's go back to the simple model with just one scalar. Because of that exponential potential, that positive exponential potential, it doesn't admit a maximally symmetric flat solution, or flat or maximally symmetric. The scalar always wants to run. But what it will do is, if you include a sphere amongst the 6 dimensions, if you say there's 2 of those dimensions form an S2, normally including an S2 would cause a negative cosmological constant in whatever the lower dimension would be, and 6 minus 2 is 4. But because of the initial positive potential, they can cancel out. And the result is this sort of solution here, you have to turn on the flux of the vector field. So there's a U1 monopole turned on also in the S2 directions. And it ends up with a flat world volume. You see dx eta. And then, of course, there's the two-sphere transverse structure and the vector field. And once this is turned on, now there are two contributions to the scalar potential, and the scalar therefore can sit quietly at its what now has a minimum, because the positive term and a negative, and the two terms actually compete and form a nice nesting place for the scalar field to sit. And of course, the parameterization has been adjusted so that that takes place at value 0. Okay, so that's the closest to a vacuum solution that the Salam-Sezgin theory has. And that's actually going to be the underlying structure that we're going to work with. Now, that was a solution of a certain 6-dimensional theory. And Miriam Svetich, Gary Gibbons, and Chris Pope then showed that it's possible to obtain that from M theory by a certain type of reduction, actually starting not so much from M theory, but from type 2A in 10 dimensions, reducing from 10 first to 7 on the 3-dimensional space H22, or from 11-dimensional supergravity on S1 cross H22. Now, this H22 is a hyperbolic 3-dimensional space. It is not a symmetric. It is not a symmetric space, but it is a cohomogeneity 1 space. So it's not a homogeneous space. So there's one important transverse coordinate that's going to be a radial type coordinate that will play a major role in the following. You can obtain it by embedding into R4 by this sort of plus, plus, minus, minus equals a constant embedding. And you can see from that it admits a natural SO2, 2 group action. And the resulting 7-dimensional theory, 10 minus 3 is 7, has maximal supersymmetry with a gauged SO2 symmetry. So this is fitting into the family of gauged R symmetry type models. The linear subgroup, when you look at the vacuum, however, is only SO2 cross SO2. Okay, so that's basically going to be how this fits into 10 dimensions. And here I have this sketch of the hyperbolic space. Rho equals 0. Rho is going to be the transverse coordinate that one uses when moves away from this waist section of the 3-dimensional H22. So you can now lift this back in the Salam-Sezgin vacuum back into 10 dimensions. And here's what you get. So this is a revision of the way that's done, which we did with Ben Crampton and Chris Pope. The 10-dimensional space with a hat given here, the dilaton in 10 dimensions, the 2 form. And inside it, you see this ds4 bar squared, which is a metric of a 4-dimensional subspace as given here. And in fact, that's a very famous space. That happens to be 4-dimensional Iguchi-Hansen metric. So in fact, this Salam-Sezgin solution, when viewed from a 10-dimensional perspective, contains a transverse sector, which is Iguchi-Hansen, and with some other coordinates, which are just S1 circles. Okay, so now we're going to try to look at fluctuations around the Salam-Sezgin vacuum from the higher dimension point of view. And we hope to find normalizable transverse space wave function. So basically what we're going to do is for fluctuation of the metric, h mu nu, so the metric becomes eta mu nu plus h mu nu. It depends on, well, we're going to take a kind of an S-wave approach to this by looking at fluctuations that depend only on this transverse radius. There are angles as well that those would give rise to YLM type higher harmonics, but they would have higher masses. And what we want to look at are the rho dependence, which is really the where the non-compactness of the transverse space plays a crucial role. So we'll look for using separation of variables. We'll look for h mu nu of x times a transverse wave function xi, and we hope to find a mass gap in the spectrum of the xi. And one sort of physics analogy of this could be if we find this, that you have two-dimensional systems embedded into 3 dimensions, for example, electrons on a metal, where the electrons can in fact be separated from the metal if you hit them hard enough by a photon or something like that. But basically, there's a work function which below which the electrons behave in a purely lower dimensional context. So one nice thing about studying the spin 2 excitations in such a situation is that general structure study of the spectrum problem, in fact, because the 2 indices on the metric eat up all the indices available to you in this theory, the resulting wave equation that you have to study, in fact, reduces to a scalar wave equation. And so we need to study the structure of solutions of the 10-dimensional Laplace equation for the solution. So if you break up the 10-dimensional Laplace equation for a scalar, as given here, it breaks up into a 4-dimensional part, a part involving these 5 angular coordinates, which basically we're going to set the eigenvalues of this delta, theta, phi, y, psi, chi to 0, because we want to look at an S-wave type structure. And then the remaining part, this delta, which involves the transverse derivatives, d squared by d rho squared. And then, of course, outside there's a warp factor called HSS to the 1/4. Okay, so that's what we have to study. In fact, this quantity deltas eigenvalue problem is the key. As I've said here, that all these theta, phi, y, psi, and chi are all compact, and we will basically employ Kaluza-Klein methods, or just look at an S-wave solutions, truncating to the invariant sector for those coordinates, but we still retain the dependence on rho. So to handle this, we need to expand fields by separation of variables into the spectrum of the transverse C problem. There could be discrete states indicated here by the sum on I, and then there will be a continuum with an integral over phi omega. Now, so we have the discrete eigenvalues and continuous Kaluza-Klein eigenmodes that we certainly expect. Now, the transverse wave function will give rise to their eigenvalues, give rise to masses as viewed from the 4-dimensional point of view in the usual fashion. So indeed, you can see here that you'll have, and in fact, with the coefficient G, by the way, is a parameter of the Salam-Sezgin solution, which also describes the circumference of the waist of the H22 hyperbolic space on which you're reducing. So that's a parameter of the underlying H22 and Salam-Sezgin problem. It also is it controls the structure of the scalar field's potential. Okay, so here we have to solve the eigenvalue problem for Xi, and now we come and look at it. Now, for delta, it's convenient to make a field redefinition by extracting a square root of sinh 2 rho factor, because the wave equation, first of all, has something that's a bit unpleasant. It has first derivative terms in it. You see, there's the derivative term. So what you can do is redefine variables in this fashion, talk about the size rather than the x's, after which you obtain a Schrödinger type of equation with the eigenvalue omega squared. And now the potential that occurs when you do this is given here. And this is an interesting potential. Note that as rho goes to 0, it gives a -1/4 rho squared structure. And people who know quantum mechanics very well, and particularly in the Russian community, Landau and Lifshitz and so forth, who know every footnote in Landau and Lifshitz, realize that this is a very special place in one-dimensional quantum mechanics. It has a kind of conformal symmetry near the origin. So let's talk a little bit about what this Schrödinger problem is. If you go to large rho, the potential asymptotes to the value 1, and in that limit, the Schrödinger equation just becomes this nice linear equation with the coefficient omega squared -1 for the psi, and then you can see, therefore, that for omega squared greater than 1, you have scattering states, e to the plus or minus I square root of omega squared minus 1 times rho. That's the continuum spectrum that is anticipated for any wave equation on a non-compact space. Now, for omega squared less than 1, however, you can have candidate normalizable bound states, which will be L2 normalizable. Now, L2 normalizable, remember that this is in terms of this psi function rather than the psi. And if you go back to the original action for fluctuations, you see you have to include the metric function square root of minus G10. And when you rewrite it in terms of psi, you find that the normalizability condition is just a straightforward L2 norm. So we demand that the mod of I squared integrated d rho be less than infinity. And in fact, the important part, of course, is the far away part for rho large. And then you see, in fact, just looking at the top, that actually you're going to have an asymptotic behavior without the I. So, and then you have to take the minus solution in order to have normalizability. So e to the minus square root 1 minus omega squared rho for omega squared less than 1. Now you have candidates. So you have candidate bound states, then from the bound states, a mass cap up to the edge of the scattering states continuum. Now, it happens that this is a very special potential, as I've said, and in fact, it belongs to a special class of integrable systems found by Puschel and Teller, and that is the Edwin Teller of the H-bomb in his years in Austria before the Second World War. So this system has a very special property that it has a unique bound state that is separated by a mass gap before the continuum of delta function normalizable scattering states that are anticipated. And for omega equals 0, the Schrodinger equation can be solved nicely, and here's the normalized result that I've given here. So what's going we then have the h mu of x's with this C0 transverse wave function correspond to massless four-dimensional gravitons on the four-dimensional world volume subspacetime. And now there's more that one can say about gravity waves, and in fact, because it's normalizable, the kinetic terms of the h mu of x will be, you can choose appropriate normalization, which I'll give you a little bit in a second, and then also the trilinear terms will give you an interactions of the h's. Also, the integrals can all be done, and you get a finite definite result for the Newton's constant. Okay, but instead of talking about that in terms of gravitons, I want to look at it from a different point of view, which is the Newtonian problem. So this is in order to try to understand better what this effective theory on the world volume and this second type of normalization. So this is not using the skeleton viewpoint of the first part of the talk. This is where we allow the fluctuations to have this very chosen by the transverse wave function equation, C0 dependence. And now let's see what happens when we try to put a source in that is genuinely localized on the world volume. So this source is not skeletonized. It is just a point source. And let's see what happens. So we're going to study this in the linearized limit. And what we want to see is whether a four-dimensional Newtonian behavior emerges on the world volume from this problem. So as we've said, the stress tensor source now is taken to be a point, not a spoke from the higher dimensional perspective. It's a genuinely localized matter source, which they can put it at the origin. Now that the full 10-dimensional situation is rather complicated to analyze. So what we're going to do, first of all, is assume as much spherical symmetry as possible, both in the four-dimensional world volume and in these transverse directions, theta, phi, y, psi, and chi. I hesitate a little bit for saying chi because it's going to have a very special role that I'll come back to. But so far, we are still going to do S-wave assumptions there. So now we consider an h mu for this point source now, delta function point source, which contains dependence on r and rho. So as spherically symmetrical as possible in both the world volume and transverse directions. So now because we've made these S-wave assumptions, the detailed analysis can begin in 5 dimensions. And but we're not going to assume any particular separation of variables form for this H-menu. We're going to try to solve it in general and see what we can do. So we don't assume here that it depends only on C0. We're going to see what emerges from the from this point source problem. So after we reduce the 10-dimensional theory down to 5, you find that what we're working with is a bosonic Lagrangian. That's all that's relevant to this problem, obtained from type 1 supergravity, reduced on, well, we have the S2 sphere directions and T3 from these various angles that have been set to 0, dependent set to 0. So we then, of course, a bunch of scalars come out with a potential given here. And now we have to see, how do we say Salam Sezgin in this language? And here's what's given at the bottom, the metric in the 5 dimensions, and then scalars phi1, phi2, and phi3, and sigma. Okay, so we have now a system with a bunch of scalars. They're always a bit pesky, but actually we have, luckily enough, it simplifies when you study this Newtonian problem. First of all, thing that we can do is, of course, we can impose a nice gauge on the 5-dimensional metric. We can impose the Dodonder gauge condition. And then you find that the phi1 scalar decouples, and so we can set it to 0. Scalars are not going to be sourced by this matter delta function. Moreover, if we're looking for time-independent solutions, you can set the off-diagonal components of the 5-dimensional metric to 0. And then after boiling it down, you find that you boiled it down to something that just involves H00 and H rho rho, with the H rho rho being related by another equation to the remaining scalar. And now the important thing is, what is this delta 5? So this is now, for the Newtonian problem, the operator that you have to study in order to find its green function. Okay. Again, it has R derivatives. So we recognize in here the spherically symmetric Laplacian for 4 dimensions, and this transverse structure involving rho derivatives. Okay, so now we try to solve the sourced green function equation. Delta 5G is now the appropriate delta function that you have to put over here, including the appropriate, the metric is given on the right-hand side with a delta R delta rho. And this theory is coming from 10 dimensions, or its reduction to 5 dimensions, which will have its finite Newton constant, kappa hat. And now let's look into near the origin and far from the origin. So if you're going near the origin, you will have this combination of coordinates becomes important. G, remember, G was a parameter of the hyperbolic underlying H22, G squared R squared plus rho squared. And then you find the asymptotic behavior as this capital R tends to 0 is given here. 1 over G squared R squared plus rho squared to the power 3/2, plus and then subleading corrections. Well, you see that this is like capital R to the -3 structure. So that's the characteristic structure of a green function, not in 5, but in 6-dimensional spacetime. Where did 6 come from? Well, that's what I said about the chi coordinate. We were looking at S-wave solutions, but actually chi is associated to rho in a very clear way. Remember the Iguchi-Hansen space that is up in the higher dimensions. And we are looking near rho equals 0, where Iguchi-Hansen has a nose, and it's smooth at rho equals 0, with an asymptotic structure R2 cross S2. And it's this R2 part, which in fact, that is being explored here by the solution. The R2, of course, has a radial coordinate, which is rho, and also an angular coordinate, which is chi. So actually, what has been found by the near field structure, near R rho equals 0, 0, the green function problem is asymptotically limiting to the green function for 6 dimensions rather than 5, and that's the R to the -3 structure. This is in fact, what you should have anticipated once you remember the Iguchi-Hansen structure, near field behavior. So now let's ask the other question about the far field. And we want to see if we can get a sensible lower dimensional Newton constant. I just remind you, first of all, in order to solve that problem, you have to decide on what the space of functions for this problem really is. We talked about C0. We haven't talked about the continuum very much. And remember that in order to have the massless gravity from our earlier work on, the effective massless gravity, linearized gravity theory, they need a C0 transverse wave function. And that was the L2 normalizable bound state of the Puschel-Teller system. That C0 ground state doesn't satisfy what you might consider the default Neumann boundary condition at rho equals 0, however, but the boundary condition is told to you by the requirement of self-adjointness of the corresponding operator. Remember this delta, d rho squared plus 2 cos 2 rho d by d rho. And we look at conditions for self-adjointness of that operator, i.e., for any two functions f and g to be in the self-adjoint domain of delta, we require in this the appropriate measure factor f delta g minus g delta f integrated with sinh 2 rho d rho has to vanish. And that gives rise to conditions at rho equals 0 and rho goes to infinity. And in fact, it's the rho equals 0 part that you have to look at specifically carefully, that you see that in fact, you obtain this requirement that rho log rho d rho minus 1 on xi has to vanish as at rho equals 0, and then of course and then the square root of sinh 2 rho xi has to vanish, has to be finite as rho goes to infinity. So this is a Dirichlet condition as rho tends to infinity, but it's a Robin boundary condition at rho equals 0. So that tells us the space of functions to be talking about to perform the expansion of the Newtonian problem. Now we can say what the transverse scattering modes actually are. What is the continuum, in other words? And they turn out to involve this family of functions with Legendre functions of the second kind. So these are the continuum xi omegas, separated from the discrete mode xi0 by the mass gap, but then we have to include all of them, because in this Newtonian problem we're not truncating or not restricting to xi0 dependence. Well, when you now construct the full green function, okay, so you can expand it out in terms of the xi0s and the xi omegas as given here, and now you look at the large rho r regime, large world volume radius, you obtain the following behavior, which differs from the near field. It involves a xi0 structure. Indeed, that's a result of that. And 1 over r dependence, which is in fact the anticipated 4-dimensional behavior of the green function. So this is, you see, a transition from, if you get close to this source, which is in fact in a higher dimensional theory, and it's going to behave like green function, the Newtonian problem of a higher dimensional theory. If you get your face right next to it, it's a bit like going next to some radio antenna. If you sit right next to the radio antenna, the electromagnetic field is very complicated and clearly is not looking like a reduced dimensional system. But if you go far away, it can settle down to a simpler system in the far field. And that's exactly what happens here. So you have a change from the potential 1 over capital R cubed behavior in the near field to a far field 1 over little r behavior. So the combination of r and rho separate, and it's a 1 over r behavior. And then, of course, with subleading corrections. Okay, now about Newton's constant. So with these modified boundary conditions, so we do have a proper localization of gravity at large little r distances on the world volume away from the source. There's still a transverse dependence on the coordinate rho, however, behaving like a log. So how do we get a number for Newton's constant? So you see there's no clear sharp association with the world volume, but it's clear that because of the logarithm, the world volume is the most important part of this space-time. As I've said before, this is not corresponding to a sharp, consistent truncation of only with the skeleton of the higher dimensions only. It is the full higher dimensional theory is participating to this. So we need to have some sense of how to kind of average and smear out near the world volume. And the natural thing to do is exactly to use the C0 structure, which is concentrated near rho equals 0. So as we did this for the gravitational gravity wave discussion, with separation into h of r times c0 of rho, we can let the your test source, your test body, so a long distance away, have a wave function which involves c0 as well. So this integrating over the transverse rho dimension, if you provide such a c0 rho profile for the test the test object, and you basically are going to get the same value of Newton's constant as you get in the three-point graviton diagram for the gravity wave problem. And here's what the result gets. This is the Newton constant in the four world volume dimensions, given in terms of, now I've expressed it finally in terms of Newton's constant all the way up in 10, involving the G factor of the waist of the H22 selection, y is one of the transverse coordinates, and so forth. That's now you see it's nice finite Newton constant, avoiding the Holland-Warner vanishing Newton's constant problem for something that is not gravity. So that's basically what I wanted to tell you about, and just give you a little overview of what I've said. Part one was about consistent truncation to a full supergravity theory, Kaluza-Klein consistent reduction to a full supergravity on the world volume with the same supersymmetry as that of the vacuum brane, which then serves as a skeleton, which doesn't change, and everything is rigid in terms of the y directions. That, however, suffers from the problem as soon as you couple to anything outside the core supergravity theory, that in that construction, the Newton constant decoupling to extra core matter would be vanishing with the Holland-Warner problem. If, on the other hand, you want to obtain a fully localized lower dimensional gravitational system, you then require normalizable transverse wave functions like C0. And that's what we then studied. So then you have to study the appropriate boundary conditions as you approach the world volume, and this is where the Robin boundary conditions came in. And if you implement such modified transverse boundary conditions, you obtain a quite satisfactory transition between near field behavior, which reveals the higher dimensional structure, and a far field behavior, which limits to four-dimensional behavior of the Newtonian problem with a 1/r gravitational potential. Okay, so that's basically what I wanted to tell you about, and thanks for your attention.
Thank you very much for your very instructive talk. Questions, please. Yes, Eva Bazin, please, Ivana, ask your question. Hi. We cannot hear. Unmute yourself.
Sorry, I forgot to unmute myself. Hi. So thanks for the nice talk.
Yeah.
Sorry?
Yeah, okay, now I've got the little thing up so I can see you. Hi.
Okay, great. Hi. Thanks again. So there are some non-supersymmetric string models in which there are like ADS vacua that nucleate branes, but these branes have a de Sitter world volume rather than a flat one. And I was wondering how much of this approach can be, recycled in this alternative case.
Okay, well, that's obviously a hot topic, and it's one that we are well aware of. I come back to this one of the reasons for this interest in Salam Sezgin is that positive potential. That is really unusual in supersymmetric structures. It falls into the family of gauged R-symmetry models, as I've said. And it has the property, of course, in the Salam Sezgin model, that when you reduce on a sphere, that the two terms in the potential will exactly cancel and give you an exactly flat space. So it opens the way to studying, can you upset this a little bit, right? Now, well, together with Honglu, back in the days before COVID, when one could still visit China, right, we spent some time trying to see whether there are any other, because there are a whole bunch of scalars that got set to 0 and so forth along the way, right? There's a tremendous amount of baggage as you come from 10 on down. You look at the other scalars, are there other solutions where you have a residual positive cosmological constant? And the answer in that case seems to be no. We couldn't find any. But there's one trick that we still haven't, we've been thinking about, but haven't been able to understand properly. Modification of the starting theory. One thing one can try to do is to go from type 2A to Romans, and then see what happens. So that's all I can answer about your question. It's really an interesting question. Of course, another thing you can try to do, of course, you can even do this in the first type of situation with the Kaluza-Klein consistent reduction. Because of the SO2, 2 gauge symmetry, you can actually divide by SO2, 2 Z, right? And thereby tessellate the system. In other words, it's like modular invariance. Like you'll have a fundamental domain, and then you integrate only over it rather than all the copies. And that, of course, that will break supersymmetry, by the way. I think that we know. But if you're not caring about that, then that's another possibility of generating a system where you could look for de Sitter solutions. That's about as close as I can come to answering your question. It's really an interesting question and obviously highly topical.
Thanks a lot.
Okay, more questions, please. I don't see, just let's wait. Maybe people will decide to ask more questions. Okay, maybe I will ask some general question. During your talk, you mentioned about black holes twice or 3 times, no more. Do you have make more comments? What happens if we deal with not brain, but with black brain or something like this? I am asking just general question.
Well, this type of, first of all, in the first part of the talk about the consistent truncation, this does seem to be a general feature that you will have a consistent truncation to a supergravity theory with the degree of supersymmetry of the underlying brane solution. So, for example, one can do it on M5 branes and so forth, and it looks like it's a completely general feature. We don't have a proof of that, but we have a number of models. You can also do appropriate reductions, world volume, diagonal dimensional reductions on the world volume and the transverse space. And you can also do vertical dimensional reductions by stacking branes. And it works in all those cases. And it looks like it's completely general. So this is a whole family of constructions that you have consistent truncations in. And as far as, I don't know if you're questioning about black holes, when I talked about black holes, I was looking at example solutions of things that you might want to do on the world volume once you have a gravity theory there. So in addition to black holes, of course, for example, with n equals 4 supergravity in 4 dimensions, you have strings. They're more than just black holes. You can have anything that you can build out of the lower dimensional supergravity. You can have a solution there, and then you can lift it up to a solution of the higher dimensional theory.
Okay, thank you. Thank you. More questions, please.
I can perhaps anticipate one other type of question, which is, what does this have to do with string theory?
Okay.
And there are two sorts of answers to that. One is in an alpha prime expansion. We know from work in the 1980s with Callan. I have to remember the list of authors: Callan, Friedan, Martinek, Harvey. That basically the leading alpha prime conditions for Weyl invariance of the string are reduced to supergravity equations. And so therefore everything that I'm saying here does correspond to supergravity solutions in that at least perturbative sense. But there is a paper by Arkady Tsaitlin and George Papadopoulos, which it actually turns out there are not very many papers on sort of brains with bent world volumes, but this is one which gives a series of explicit, concrete examples where the conformal invariance conditions to all orders in alpha prime are satisfied, and it forms a subset of the solutions that we look at. So there is clearly a relation of what we're doing here to general properties of string theories, and that's a comment I can make. But that it seems to be you have to decide whether you're going to talk about string theory in the perturbative sense in alpha prime, or whether you're going to try to talk about string theories in to all orders.
Okay, very good. More questions, please? Maybe I ask one more, some general questions. What do you think? What is a more urgent problem in this framework of always what you said as? What is more?
Well, I think one of the, as I've said, the positive potential of the Salam-Sezgin solution is what is particularly interesting from the point of view of searching for systems. There are two attitudes to that. One is stop worrying about de Sitter space per se, but cosmological applications of all of this, because you can also deal with, as also in the weak gravity conjecture and swampland discussions, make sensible cosmological models with not with a stationary scalar field that gives a de Sitter solution, but with a running scalar field, especially if it's not running very fast anymore. So a slowly sliding small scalar field, in fact, is attractive for giving you a tiny cosmological constant, and try to make solutions that work with that kind of setup. So this, in fact, does give rise to a natural family of models. Well, in other words, you don't have to do the same two-sphere reduction or cancel it completely. You can have the scalar field not sitting at its stationary value, but approaching it and look at cosmology. So that's another attractive field for applications of these types of systems.
I see. As I understand correctly, we discussed mainly static solution. Is true?
Yes, here for some, in order to discuss the Newton problem, one has to simplify it as much as possible. Yes.
And what about with no knowledge of your solutions, try to construct some shock wave solution, something like this? So it's difficult.
Well, so one thing that I didn't talk about in detail, but which I alerted to, the leading behavior on the effective theory in terms of these the H mu nu, not putting now a Newtonian source, but just looking at their interactions amongst themselves. You have a Pauli-Fierz leading kinetic structure, and then you have trilinear structures which give rise to a Newton's constant. I gave you exactly the same value I referred to. You get the same number as in the Newtonian problem, so that's a lower world volume gravity, which of course that doesn't have to be static. Those are gravity waves, and then then you can look at the higher order behavior. One special feature of this, however, which I also didn't have time to talk about today, thanks to Peschel and Teller, you have this integrable structure. And when you talk about higher order terms, you don't have to just wave your hands. You can actually do the integrals, right? So we can do the integral. That's why I did the integral to show for the trilinear structure for H mu nu. Once you have that, you say, aha, this is our effective gravity. It's just Einstein's theory. Well, it's just Einstein's theory with a footnote, because when you look, having acquired the Newton's constant that you get at the third order, at trilinear in fields, if you go to the fourth order in fields, you also can do the integral. You get the coefficient, and you ask it, is it the expected kappa squared coefficient that you anticipate at fourth order? And the answer is no, it's not the same number. So this is what I referred to as a covert kind of symmetry breaking that only appears at higher orders in the expansion in gravitational fields. And one can understand, I mean, that's another longer discussion about how this is happening nonetheless consistently with the original higher dimensional diffeomorphism invariance, and it does work out. But when you look at the effective theory in the world volume, it's not quite Einstein gravity. It is a massless gravity together with a bunch of, the anticipated vectors and scalars that you get from any Kaluza-Klein type of reduction. But its gauge invariance properties are special. And basically what's happening is that one of the vectors of the Kaluza-Klein, this reduction, in fact, is acting like a Stuckelberg type field, which is what's patching up the difference in the coefficient of the fourth order and higher order terms. But you have to go to that high order in the expansion of the effective theory before you see this difference from Einstein's theory. So that's another place where, by the way, I don't know the extent to which the fourth order terms, the h mu nu to the fourth terms, have ever been really measured in gravity. It's certainly not in terms of gravity wave interactions, but it could very well be that is something that with colliding black holes we now have some handle on. So there's obviously, that's another direction for applications of this study to see. So all of this is about what's it like if you live on a brane world volume that is embedded into a non-compact transverse space.
Mm-hmm.
Without yet realizing the transverse directions are there. You can, and unless you get your nose very, very close to a source where you start seeing this higher dimensional dependence, what are the indications you can have that that the higher dimensions are actually there?
Okay, thank you. More questions, please? That's Ravan, please ask your question, yes.
Hi, Kellogg. Thanks for the very nice one. Well, I have actually one generic question which I always confuse about. Thing is, you mentioned Ricci flat solutions, right? So, well, which are easy to look for and easy to solve.
Once you've seen how to organize the ansatz, then you see, first of all, just with straight Ricci flatness, but then with the extension to supergravity. So that's why I showed you the decomposition of the Ricci tensors, the full Ricci tensors into the Ricci tensor on the world volume and the Ricci tensor in the transverse space. But you see that you are now entitled, as Chambling, Hawking, and Real did. Once you see R mu nu equals 0, Stephen Hawking is immediately going to jump on a black hole. Okay, that's an example.
Yes, but that's easier to look at. But when we complicate gravity theory, it is expected that we find more solutions. I mean, for example, your R plus R square plus R mu square.
Oh, well, okay.
Theory, there are more solutions you found. And in supergravity, which is structurally much more complicated than fourth order gravity, and there should be even more, black holes should be even more complicated in general. I mean, from general intuition.
Of course, I was starting from a pure second order supergravity theory, type 2A, type 2B, or M theory in 11 dimensions with just second order terms, right? This whole discussion was limited to that. One thing I should say, by the way, for anybody who likes talking about consistent truncations, which of course is mathematically great fun, but you take into account corrections, precisely the terms that you are referring to, the curvature squared terms and all the higher ones, are going to ruin your consistency. So your context of looking for lower dimensional physics is much more like the second part of my talk, trying to look for an effective theory below some sort of cutoff. Here, the cutoff was given by the mass cap, right? Depending on this parameter G that I had for the belt, the waist of the H22 space. But that, in fact, I think is really the generic situation that consistent truncations are mathematically interesting. And that's why I talked about this. But it's almost certainly not the full story, because any quantum corrections, every string theories also produce curvature squared term corrections, right? So
Yeah.
the consistent truncations are fun, but they are of maybe limited physical application. So curvature squared terms, yeah, you can do that. And then the whole first part of my talk becomes irrelevant, but the second part of my talk is still there. It's just that the details, of course, will become complicated to work out.
Okay. Understand. Thank you.
Okay. More questions? I don't see any. Maybe the people are very tired. Let's thank Kelly once again for very instructive talk. Thank you very much. And don't forget to send us the transparencies of your talk.
Yeah, sure.
Yes.
Happy
Okay.
to.
Thank you very much. Thank you.
Yeah, thank you very much.
Thank you.
So how are things for you, Ira, in Moscow?
Oh, it's complicated. It's difficult to say. After this COVID, of course, we had now accustomed to work at home.
Yeah.
So it's
For us
terrible.
too. Yeah.
Yes, but in all other respects, it's difficult to make any comments. Yes.
Yeah.
I prefer to
And
not.
how is Andrei Slavnov? I understand he's not well.
No, it is not good. Definitely not good. Yes. Yes. Unfortunately.